Hey everybody, welcome to Goldendale Observations number 16. Tonight we'll be talking about gravity waves and also a facility that's not too far from here that you might be able to visit someday where they actually observe gravity waves. This particular topic is not random. We are actually kind of following up on last week's show where we talked a bit about Einstein's relativity. We talked a bit about how solar eclipses were used to help detect the curvature of space-time and the bending of light by that curvature. That was a very clever experiment. And LIGO, which again we're going to be talking about tonight, is also a very clever experiment and also a very modern experiment. And it comes almost 100 years after Einstein's original supposition that the bending of space-time might actually ripple, create waves in reality itself. It's very kind of a romantic story, really, that a century after it was predicted, it was eventually confirmed. We'll be talking a bit about that, and hopefully answering some basic questions about how it all works. Hopefully by the end of the show, you'll understand a little bit more about what gravity waves are and understand how we detect them. So let me bring up the chat really quick. As always, my name is Troy Carpenter, and I strongly encourage you guys to ask questions. And comments. Last week we had a bit of delay, we had a bit of latency, so I'm going to see if we can improve on that a little bit tonight. On that thought, hold that thought a second. I'm going to bring up my interface, and I'll see if you're chatting yet. Anybody out there? Hello from Tumwater. Yeah, that's good. Someone's out there. That's nice. Looks like we got 29 people viewing right now. Yeah, so let me know if you can hear me all right. It looks like you can. I'm going to do a little experiment. Yeah, there we go. You know what? This might be a better solution. This might be a lower latency option. So, on that subject, let's do an experiment. I'm going to say I'm going to do a countdown. I'm going to make a beep, and I want you guys to type in the chat when you hear it. Beep. I'm watching the chat. Oh, good. All right. That was back to normal, I'm happy to say. That was less than 7 seconds. Good. Well, in that case, I fully and completely encourage you guys to ask questions and make comments tonight during the show. As I say every week, this is a public observatory. We exist for sake of education. If you leave the show tonight without learning something, I have failed you. To prevent that from happening, ask those questions, make those comments. So, to continue the, oh good, yes, I agree. It's good to know that we have low latency. All right, now, to continue my normal operations kind of tradition here, I'd like to start with a question. So before I start talking about this topic, which is deep but not, depends on how far we go into it, are there any basic questions you want to get out of the way? Let's see, let's answer one question, then I'll start talking a lot. Go ahead. While you do that, I'm going to tidy up my files a little bit. Let's hear some questions. Smaller bottle of water tonight. Yes. I should start advertising on these. You know, it's funny you mentioned that because I want to get branded water bottles for the observatory, and then I could be like, you can have yours if the price is right. Perhaps a fundraising tool in the future. Branded water bottles. All right, so do we have any questions that don't involve water bottles? Nothing? No questions? Any space events, any current events you want to talk about really quick before we get going? All right then. So silence it is. Let's see, where to begin? This is another topic that involves, oh wait, who was the first known astronomer? Oh, I don't know that. I do not know the answer to that question. Do you know the answer to that question? Is that a quiz for me? I do not know who the first... Well, it depends on how you define astronomer. Astronomers used to be conflated with astrologers. They often were soothsayers and mystics. Sometimes they were also the medicine man. So it's hard to say when the first disciplined astronomer was born. Although I will tell you, we're going to talk about Isaac Newton a little bit tonight. And he's sometimes credited as being the father of modern science. But other people say he was the last of the magicians. A lot of people don't know that even though Newton was a super genius and his math essentially solved the universe, he was also an alchemist. and he tried to do a lot of mystical things, including crafting the legendary Philosopher's Stone. Of course, he failed to do this. And he had a lot of other mystical ideas, too. So one could argue that everyone after Newton was a disciplined astronomer. What's the next big event? You mean like a space event? Oh, there's a few lunar eclipses this year. If you're asking what our next show is about, we're going to be talking about telescopes and how they work, and maybe even which kind you might want to buy. So that's fun. Anyway, yeah, so Newton may have been the first of the disciplined modern astronomers or the last of the mystics. It's up to your point of view and your interpretation of history. Okay, so Galileo is interesting. Someone pointed that out. He popularized the use of telescopes, and he was quite disciplined in his observations, and he did come to some important conclusions about the universe. For example, he was one of the first to start talking in earnest about reference frames, which were very important, something that we actually are going to talk about tonight. That was very modern of him. It was very forward-thinking of him. The notion that your frame of reference is very much important when it comes to understanding the observations you make. If your reference frame is moving, for example, and you're observing another moving frame that is not related to yours, not linked or synchronized with yours, that's going to create a third vector that is not going to be either one of the experiences of an observer in either one of those reference frames. So that was quite advanced of Galileo to figure that out, long before we were talking seriously about such things. All right, so you seem to quote Einstein theory a lot. How does it seem to apply to you so much? Well, because Einstein did for us in the modern age what Newton did in the 1600s, and that was essentially solve the universe. You see, Newton, and actually this is not a tangent. This segues perfectly into what we're going to talk about tonight. Newton's observations and his extraordinary math made sense. Suddenly, everything we were observing in the sky was sensible. Suddenly, we could predict the future using his math. So that's why Newton was such a big deal. Einstein continues to be a further big deal because Einstein's math, his relativity and special relativity, and a few other contributions, further solve the universe. They help us understand the observations we make. Suddenly, the universe makes sense again. Because you see, during the time of Newton, everything worked out until the late 1800s when we started to discover problems. We started to discover discrepancies in Newtonian dynamics that had to be explained. Einstein's relativity helped explain those unusual observations. The example I always use is the precession of Mercury's orbit, which did not behave as Newton predicted, but it did behave as Einstein's relativity predicted. We talked about that quite a lot last week. Now, it's not always appropriate to talk about Einstein, but he's very popular. And if you're studying this tough stuff from a 101 level, he established a lot of frameworks that we can build on and discuss. Of course, literally thousands of other scientists, physicists, researchers contributed to our modern understanding of science. For example, the apparatus we're going to be talking about tonight, Ligo, that was pioneered by a guy named Rainer Weiss, although he is very humble about the fact that he did not single-handedly invent the thing. His work was based on the work of literally thousands of others, and he never hesitates to remind people of that fact when they want to give him all this praise for LIGO. But he says, oh, it wasn't just me. There's a lot of really clever and really hardworking people around me, before me, and after me that made it possible. Yeah. He's still alive, too. All right, that was fun. So, why does tide occur on the O? What does that mean? Well, I like that. Einstein reconciled physical motion and light. That's interesting. He also determined that the speed of light was very important when it came to the behavior of the physical universe, not just matter, but space-time itself. We're going to talk about that tonight. Let's see. Oh, you know what? Let's answer this question, then we're going to get to it. When someone asks, what is the greatest advancement in the past 5 to 10 years for hobbyist astronomers? The cheapness. It's become possible to mass produce good quality optics. And suddenly, a regular person who's not a serious astronomer can afford a pretty darn good telescope. In fact, I am amazed at the quality of some of these mass-produced telescopes coming out of China for a few $100. It wasn't that long ago that if you wanted to buy a good telescope, you had to spend thousands and thousands and thousands of dollars. So yeah, one of the great revolutions in the last decade or so, cheapness. Telescopes are becoming very affordable also. The computer brains are getting cheaper, and so you can buy telescopes with computerized mounts that are actually good at what they supposedly do, which is find objects and track them. If you'd ever had the misfortune of buying a computerized mount from less advanced time, you'll find that they're quite annoying to work with and even frustrating. And that's one of the reasons I often recommend people not buy computerized telescopes and instead go for one that's manually pointed. All right, let's get down to it. So, like I said, it wasn't off topic. It was a good segue. Isaac Newton's universe made sense, and specifically we're going to talk about one of his important rules. By the way, here is the guy, Isaac Newton. You know, hold that thought a second. Yeah, let me see here. I'm going to give you a nice picture of his handsome face in case you forgot what he looked like with his long flowing hair. Oh, I got my... Sorry, buddy. There you go. So, Isaac Newton, the father of modern physics, or whatever you want to call him, his book of math, the Principia, was very, 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 very influential. And like I said, in this book, he established, among other important things, his laws of motion. Tonight we're going to talk about his universal law of gravitation, and what's right about it and what's wrong with it. So let's read it. Every mass point in the universe attracts every other mass point via a linear force proportional to the product of the two masses and inversely proportional to the square of the separating distance. This is the equation that proves that. Here's a little cartoon drawing to help you understand a little bit better. We don't have to go into this in too much detail tonight, though, because Newton made a mistake. The big G here, gravitational attraction, gravitational constant, was, in Newton's view, an instantaneous phenomenon. Newton believed that this gravitational attraction between all bodies in the entire universe propagated instantaneously. Now let's talk about that. Yes, and so, very good, Ed points out the inverse square law. Newton did correctly point out that as distance increases, intensity of interaction decreases exponentially, not linearly. By the way, that inverse square law applies to all sorts of things, including electromagnetic radiation. The farther something is away, the dimmer it becomes, and it becomes dimmer exponentially, not linearly. Anyway, so the big G here, gravity, was thought to be instantaneous. Now, if this were true, then something interesting would happen if the sun suddenly ceased to exist. If the sun suddenly ceased to exist, Earth would go rocketing off into space in a straight line, carried forth by its inertia, right? But Earth would not actually instantaneously leave. It would not instantly rocket away. In fact, it would take about 8 minutes to do it. Who could tell me why? Why would Earth suddenly take off after 8 minutes of the sun no longer existing? Any thoughts on that? It's kind of a fun topic. I like that. That's true. Let me put a video on the screen here. So, okay. Someone said, well, yeah, but see, gravity. Oh, speed of light. Okay. So, gravity is what we're talking about, and Newtonian equations in this context apply to gravity. But Newton believed it was instantaneous, and Ed here points out that it's actually limited by the speed of light. Now, something we talked about last week, to answer the question again about why we talk about Einstein so much. Einstein realized that gravity was not some kind of sucking force, like an attraction force, but rather it was let's say, an illusion, if you will, or a phenomenon only experienced because mass bodies bend space-time. You might recall this video from last week. This is a relatively accurate three-dimensional representation of what really goes on as a mass body moves within space-time. As you can see, these reference frames, if you will, these individual quantas of time and space are being compressed by the gravity. Yes, good. The bending of space-time is not instantaneous. It propagates through the cosmos at the speed of light. This is a very big deal. And this is the primary difference between Newtonian physics and Einsteinian when it comes to the prediction of motion. It was the phenomenon that stymied Newtonian solutions to our observations. And again, I mentioned the Mercury story, but it's not just the Mercury story. It also explains things like the Doppler shifting of light as it passes through space and passes by numerous heavy bodies, or perhaps emanates from heavy bodies. Now, we talked about the bending of space-time as you're seeing in this video, but Einstein's equations also predicted that space-time itself should ripple, that it should experience waves. And this is actually kind of a neat story because Einstein was highly pessimistic about his prediction. He felt that it was probably correct, but he believed that we'd never prove it. And Einstein's reason for thinking that we'd never be able to prove gravitational waves exist are several. First of all, in Einstein's day, we were not aware of the fact that there were extraordinarily heavy objects in the cosmos, like black holes and neutron stars. These were theoretical bodies. Neutron stars, we had an inkling of their existence. Black holes were still something you showed someone on paper to kind of joke about the problem of singularities. Like, aha, wouldn't it be strange if an object had infinite density? That's ridiculous. So, we had not proven the existence of a single black hole. So right there was one problem. Einstein thought there weren't any objects in the universe, or we didn't know of any objects heavy enough to produce detectable gravitational waves. He also was aware that we were certainly unaware of any objects being close by like that. And furthermore, he realized that the effect of gravitational waves would be very weak. So he thought, there's no way you can build a detector to detect these waves because they're going to be so absolutely subtle, so unbelievably weak, that although we can prove them on paper to probably exist, we will never be able to measure them empirically. But scientists never accept that. We won't just predict something on paper and say, oh, well, it has to be true because the math says so. Because the universe is a surprising place. And when we rely only on mathematical models, sometimes we miss things. So there's been a great interest in scientific communities for a century plus to prove the existence of gravity waves. And for most of the time, it was a technological issue. You couldn't construct an apparatus sensitive enough to detect the unbelievably tiny perturbations of space-time that would result from mass bodies moving through space-time. Now, speaking of moving, let's talk about this. The way a body moves will affect its emission of gravity waves, if they exist, and we'll get to that. So let me show you here. I have a screwdriver in my hands. Now, let's say the screwdriver was enormous. Let's say it was the size of a planet or a star. If it was rotating like this, it would not actually emit gravity waves. Gravity waves are emitted when there's a change in space-time due to acceleration. If this screwdriver were spinning like this, if I can do that, there we go, close enough. Let's say we have let's say the handle is the heavy part. Now that handle moving around in space-time is going to actually create gravity waves. Now, because this screwdriver has very little mass, the gravity waves will be unspeakably weak, but they will exist. I should tell you right now as we get into this, for the most of the night, we're going to be talking about things like neutron stars and black holes, and that's because these are bodies which are exceptionally heavy enough to emit gravitational waves. It's not so much a matter of physics or physical law, it's more a problem of technology and our ability to detect these phenomena. So I mentioned a guy named Rainer Weiss. Back in 1968, he came up with an idea. He thought that you could construct an interferometer, and we'll talk about what that is in a second, using laser beams that could be sensitive enough to detect gravity waves. He essentially was scaling up a device that you could buy on a tabletop size outfit for detecting, for example, the vibration of a piece of equipment, like a jet engine that was out of balance or something. He thought, well, if we could make this instrument huge, like miles long, maybe we could become sensitive enough to detect gravity waves. So way back in 1968, he came up with this idea. It wasn't until 1990 that they funded his idea, and he had the audacity to push it through. It was so ambitious, it's hard to believe. I'll get into the detail in a few minutes about just how ambitious it was and how unlikely it was to succeed. But before we do that, we have to talk about how it works. We need to talk a little bit about the science of interferometry. As the name suggests, it involves interference. I'm going to show you an example. Let's first, as we discuss interferometry, we're also going to talk about the concept of resolution. Let me show you. Anybody know what this is or where this is? Anyone know what this picture is from? Anyone know where this is? I bet you do. Yes, very good. The VLA, the Very Large Array, which is an array of radio telescopes in New Mexico. Now I'm going to use, very good, radio telescopes, that's right. I'm going to use these as an example of what I'm talking about. Yeah, southwest, that's right. Oh, hey, here's a question. Why put it in the southwest? Why put it in New Mexico? Why not put it in a more convenient location? Like, I don't know, right next to New York City or Los Angeles. Why would that be a terrible idea? What do you think? Why does it end up in the southwest? What do you think? By the way, that's not a tangent. This has to do with something with our show tonight. Interference, right. Radio telescopes, if they're going to do the job, need to be very sensitive. That's why they're so big, by the way, one of the reasons they're so big. And if you had it next to a city, obviously it would be receiving all sorts of radio interference, not just from actual radio devices like, radio stations, TV stations, Wi-Fi, whatnot, but also from things you wouldn't think about, like the ignition coils of automobiles. A lot of people don't know that you're not allowed to drive a gasoline engine car around a radio telescope, most of them anyway, when they're actually doing observations, because the ignition coil produces too much radio noise. That word noise is going to come up too in a second. When we talk about noise, we're not necessarily talking about sound, are we? We're talking about undesirable data, if you will. The universe is a noisy place. All right, so let's go over a few concepts. The Very Large Array is a giant interferometer. But before I explain what that means, let's talk about why the dishes are the way they are. If you want to measure something that is very subtle or slight, you need to measure at very high resolution. You need essentially very fine data. You need high fidelity data. So essentially you need more information. People mostly know that the reason we construct giant telescopes, like these for example, is so we can collect more light. And by the way, yes, radio waves are light. They're part of the electromagnetic spectrum. But what people often don't know is another reason we construct telescopes to great size is so we can maximize the opportunity to collect different information. So, for example, I've shown you a picture a few times, but I just find it so delightful that I just can't not show it to you. Here's a picture of the planet Jupiter twice. You know what? I'm in the way. There we go. So in this image, we see Jupiter in visible wavelengths, and we see Jupiter in radio wavelengths. Which of these two images is higher resolution, do you think? That's kind of a silly question. Which of those two objects, or rather images, of Jupiter is of higher resolution? Yeah, I also like this picture. I think you'd all agree the one on the left, the visible wavelength image. Yes, I agree. The left image is sharper, so to speak, higher resolution, because it literally contains more information. The reason that that Jupiter image contains more information is because visible wavelengths of light are smaller, and so a given size collector can literally collect more of them because the waves are tiny. Radio waves can be huge. They can be feet across, even miles across, and so even with a very large detector, you end up getting fewer photons. Essentially, you get less information. Think about that a little bit. Let me go back to that picture of the VLA. Now, here's how it works. If you have, I got my mouse on the screen here. Pretend my mouse is a photon from deep space. Photons, quanta of electromagnetic energy. Here comes my photon. And it strikes the dish. Okay, then we measure that. Another photon comes by. Also strikes the dish. Now that photon happens to exactly perfectly match the previous one in terms of what data it represents. As a result, we have not obtained any new information from that second photon. We've simply obtained more of that same quanta of information. So let's say we have more gain. We have a brighter image, so to speak, a higher luminosity data figure. But because we haven't obtained new information, we have not increased our resolution. One of the reasons we make detectors big is so that you maximize the chance that photons collected will be different. So let's say we have a photon coming down over here, and another photon coming down over here, and they're different. Now we have two different pieces of information. We've now, let's say, doubled the resolution of our image, so to speak. Does that make sense? You want to increase the opportunity for the data to be different. The higher the resolution obtained, the finer the observations you can make, right? Again, this is very important if you're trying to detect extremely subtle phenomena. Now, let's talk about interferometry. I told you that the Very Large Array is an interferometer. One of the other tricks we use to find more information is by letting two signals cancel each other out. Anything that survives the cancellation process is new info. Let me show you what I'm talking about. So here we have incoming signal. And then we have what we're calling the cancellation signal. Now, the cancellation signal is actually the same signal, but we have deliberately delayed it by some mechanical or artificial, maybe active means, so that even though it's the same information, the waves are now out of phase with each other. They're out of time with each other. Now, when you transpose waves that are the same, but 180 degrees out of phase with themselves, they cancel. This is called destructive interference. However, if you have the incoming signal and the cancellation signal, which again is the same signal but delayed a little bit, and there's, let's say, a little bump right here, that bump will not exist during the cancellation wave, and so that little bump will survive, and you'll get a little blip in your data right about here where my mouse is. So instead of a zero effect, suddenly data will appear as if from nowhere because it survived the cancellation process. This is interferometry in a nutshell. You're taking signals that are identical or almost identical. You're allowing them to cancel each other out, either passively or actively, depending on the technology. And anything that survives that process is useful information, useful data. You have increased the amount of information by doing this. Any questions about that? I'm going to talk way more about it, but that's just a concept. We're talking about canceling out signals that are the same to reveal those which are different. And again, we want different signals, we want different information because that's actual useful data. Okay. Let's talk about LIGO. So we have the facility here in Hanford, Washington, another facility in Livingston, Louisiana. And you have these long tubes. See this? Those tubes are very long, 2.5 miles each, and they are completely evacuated. So there's no air in them. They're a hard vacuum. It's like outer space inside of those long tubes. And we shoot lasers through those tubes. And because they're perfectly evacuated, the laser beam should not be disrupted by anything going on inside the tubes. And we do something very clever. I'm going to pause this. As you can see, we have a tube here converging on the facility. We have another tube converging on the facility. And a lot of important stuff goes on inside here. Let me show you a type of interferometer that uses lasers. So this basic Mitchelson's interferometer is, like I said, the kind of device that one might see in an engineering lab. The way it works is this. You have a laser beam. Lasers are famous for shooting very specific wavelengths of light coherently. So the photons are all going the same direction. They all have the same frequency or wavelength. Those laser photons encounter a beam splitter, which is essentially a translucent mirror. Some of the light bounces off the mirror, and some of the light passes through the mirror. It strikes another mirror, in this case, comes back, bounces off the back side of the mirror, and hits a detector. Meanwhile, this laser light goes up, bounces off this mirror, bounces back, goes through the beam splitter, and again, hits the detector. So like we were just talking about, we have two identical signals, so to speak, that are deliberately out of time with each other, out of phase sync, because we have physically moved one of the mirrors farther away than the other one. So we have introduced a delay on purpose so we can create that 180-degree phase mismatch. As a result, this detector should essentially detect nothing because these two laser beams, which come from the same source, are canceling each other out. If anything were to go wrong during the process, if anything were to change, for example, then that would be detected because it would be a peak in the signal which was not reproduced in the cancellation wave, and it would make it through, and we would detect an extremely fine, hopefully fine detail in whatever we're observing. Now, in the case of LIGO, it's using a laser of a wavelength of 1064 nanometers, which happens to be in the infrared band. So this is a wavelength of light which is below human vision. And yet, even though that is infrared light, which we consider relatively low frequency, it is actually a very high frequency. It's about 200, it's over 200 terahertz. So 200 terahertz is 200 trillion oscillations per second. So, supposedly low energy or low frequency infrared light is actually oscillating over 200 trillion times per second. And actually, I have an exact number for you because I wrote that down. I thought it was quite interesting. Yeah, 282 trillion hertz. Now, before we move on, I need to tell you what hertz mean. This is one of those things everybody should know. So if you don't know this, let's get tuned into this a little bit. Hertz is a measurement of cycles per second, named after Heinrich Hertz. Most of you probably know the frequency of alternating current coming out of your outlet. It's 60 hertz in the United States, 50 hertz in most other countries. So if your outlet is putting out 60 hertz AC, that means that the current is alternating 60 times per second. Again, hertz is essentially short for cycles per second. So cycles per second, in this case, outlet, very low frequency, 60 hertz. In the case of infrared lasers like the ones used in LIGO, we're talking about 280 trillion hertz. So that's, just so you know, that's 280 million hertz. So that wave that I showed you in the previous image is oscillating that quickly. So imagine up and down 280 trillion times per second. Now there's a reason we're using that high frequency, because this wave is trying to help us detect something incredibly subtle again. So what we're doing is deliberately using a quanta of energy that we know pulsates, in this case if we're measuring it, counting it as pulses, hundreds of trillions of times a second, and we're giving it a long path to increase the ability to detect whatever it is we're trying to detect. I'm going to show you more in a second, but keep that in mind. Yeah, so Ed here talks about megahertz being a million cycles per second. Yeah, so kilohertz, 1,000. Let's talk about the tone that you hear on the TV, like the color bars, that's 1 kilohertz. That's 1,000 oscillations per second, which suddenly seems like a very low frequency when you think about it, compared to the infrared waves we're talking about. It hurts my head. That's funny. So we are attempting to detect nothing less than the compression of the entire LIGO facility as it is squashed and stretched by space-time itself oscillating in response to heavy bodies moving within the cosmos. Because these bodies are very far away, for example, sometimes billions of light years away, the phenomenon is incredibly slight. So I'm going to show you a hyper exaggerated example. You can see here what's happening is essentially the entire LIGO facility is being stretched and squashed by gravity waves. We're trying to detect that. As the laser beam travels down the tube, if the entire tube suddenly changes length ever so slightly, then that cancellation wave will not match up with the original laser wave at the detector, and we will get data. Now, I told you this is a scaled up version of something you might see on a tabletop. So imagine that this is not miles long. Imagine this is about this big. You might see an instrument like this in an engineering lab where they're trying to, for example, measure vibration. So let's say you had a jet engine that was out of balance. And so when it runs, it shakes like that. Well, a laser interferometer like this would allow us to very precisely detect vibrations. Now, vibrations that you can see or feel or hear are obviously going to be very easy to detect. So you would buy a laser interferometer for things that you also couldn't just obviously detect with your hands or your eyes. But again, the tabletop unit would only be sufficiently sensitive for ordinary things like our gizmos and gadgets that we invent. In the case of LIGO, we're trying to detect the compression of space-time itself. Now, I told you that the tubes are 2.5 miles long. That is actually nowhere near long enough because they do something clever. Check this out. This is a basic Mitchelson interferometer. This is actually the design they use in LIGO. 4-kilometer Fabry-Perot cavities and power recycling mirror. They have added to this device special mirrors which force the laser beams to bounce back and forth within the tubes, essentially making them longer. In fact, it makes them about 300 times longer. And so suddenly that that 2.5 mile long tube appears to the laser beam as 750 miles long. Think about that. So now you've just essentially increased the size of your detector for free. Not really free because those lasers cost money. Those mirrors cost money, but it's much better than trying to build a tube that's 1,000 miles long. Isn't that clever? Yes, 300 bounces. Now, the reason these are not ordinary mirrors, but etalons, is they are also intended not only to make the laser beam go longer, they're also intended to make sure that it remains the right frequency. So these etalons actually cancel out wavelengths that are not within spec. Now, I'm holding one in my hand here. You might remember this from the solar show. This is the same concept. Same type of etalon, actually. This one is what's referred to as a hydrogen alpha etalon because we're using it to passively cancel out all wavelengths of light except for those emitted by ionized hydrogen. So this is a solar filter because the sun is made of hydrogen. So same concept. All this is a stack of glass plates which have special coatings that are very, very, very precisely engineered and manufactured so that their spacing is extremely deliberate and exact, and their thickness is exact. And this device, again, passively, using destructive interference like we just talked about, can reject all wavelengths of light except for those you're interested in studying. So they're doing the exact same thing in this device. But it's much more expensive. These mirrors are much more costly. Speaking of which, let me show you something you might find kind of cool. Here's a video about them cleaning the optics. So let me show you some things here. This might impress you. Here's one of the labs where they clean these mirrors. I want you to see what they look like. As you can see, this was provided by Caltech. This is one of the beam amplifier assemblies to make the laser beam stronger via a photon cascade. Here's one of the mirrors. It is made of incredibly pure material. Now look what they're doing here. They're pouring this substance, this product on it, which congeals into a gel, which you then peel off, and it takes all the dust with it. It goes without saying that for this instrument to work properly, these pieces have to be incredibly clean. Yes. Oh, yes, and keep the vacuum in the tubes. Well, we have to do that, of course, yeah. Now, James points out that it's amazing they can keep the laser running all the time. The laser is actually LED-based, believe it or not. It's not a gas discharge laser. And as a result, they tend to be quite reliable. Look at that. You can see the special coatings there. Those different colors. Look at that. You can see the heat from her hand there. This is how they clean the optics. It has to be essentially perfect. Look at that. There's a chamber for vacuum sealing to install it in the machine without introducing any air. Aren't we clever? So I just wanted to show you what one of the mirrors looked like. So let's see if we understand so far. The detector is constantly being squashed by the oscillation of space-time, and we can detect the extremely tiny variations in the size of the facility because those laser beams, which again oscillated over 200 trillion times per second and are flying through 750 miles of tube space as far as they know, will be shifted ever so slightly. They will be ever so slightly different from one another when they both converge on the detector. I've gone over a lot, and some of this might be kind of foreign to you guys, so feel free to ask questions. I have a lot more to say, but feel free to throw some questions out there. I'm going to give you a second. Let's hear some questions. Questions, any questions? Well, looking at large rare events first, yeah, that's right. Okay, so let me tell you a story. LIGO was actually not the first facility to detect, at least indirectly, the presence of gravitational waves. That actually happened in the early 1990s. But notice they say direct. We indirectly detected gravitational waves in the early 1990s in a very clever way. I'm going to tell you about that in a second. Oh, Laser Interferometer Gravitational Wave Observatory. That's what LIGO stands for. I should have told you that. How do they compensate for seismic activity? That's a good question. So, there's another technology piece I haven't gone over yet. In addition to all the cleverness with the lasers and the mirrors and the very high dynamic range detector, because LIGO is so sensitive, it also generates a lot of noise. And again, when I say noise, I'm not talking about sound, I'm talking about data noise. In fact, it generates so much noise that the data would be useless to a human being. In fact, LIGO is only able to work because it has actual artificially intelligent computers, essentially algorithms, that analyze that data and look for the telltale signs of an actual event taking place, a gravitational wave event. Now, this is kind of a... So you lost me. If I lost you, feel free to ask questions. I want to make sure we get it. So radios, when you listen to a radio, let's say an FM radio, and you turn it on, it's going to make lots of noise. You hear all the crackling, right? But let's say you're trying to listen to a very weak station with your radio, and it's crunch, crunch, crackle, crackle. But you can make out the sound of a human voice, or maybe music. That's something that human brains are very good at. We're very good at measuring patterns. We're very good at finding patterns. And to a human being, it's actually almost easy to recognize a human voice talking, even when it's drowned out by the loud noise of radio interference. A human being could never detect the type of waves we're talking about for many reasons. First of all, a human would not recognize these sounds as familiar if they were sounds. But second of all, the signals are so weak that you would fail at attempting to even observe them. You would just see a bunch of signal noise and you wouldn't get any useful information out of it. All right. So it looks like someone's following up. So the lengths of the waves help us to determine and measure gravity. The waves, the length, so to speak, the wavelengths, the gravity waves, illustrate how powerfully space-time has been disrupted. I'm going to show you some cool videos in a second that helps you understand that. So a very violent event between two very heavy bodies, black holes for example, might create intense gravity waves which are easy to study. But small bodies also produce gravity waves. It's just that they produce them to such an extremely weak degree that we would never be able to measure them using current technology. Let me give you some idea of how absolutely minuscule these signals are. As I said earlier, this video you're watching is dramatically exaggerated so you can understand the concept. But we're talking about a device that is capable of measuring a deflection in its geometry less than 1/10,000th the diameter of a proton. Now that is mind-bogglingly small. If you were to scale that up, a light year of distance would entail less than a millimeter of shift. That is an impossibly tiny shift in size. Something that should not be detectable. And when I first learned about this, I'm like, this can't be real. I must be misunderstanding this. The skeptic in me was like, how could humans possibly invent a device that could detect a deflection that minuscule? I want to repeat. It can detect a geometric distortion of the entire facility less than 1/10,000th the diameter of the charge area of a proton, of a single subatomic particle. The reason it's possible to be this sensitive is because, as we discussed, we artificially increase the length of the tubes via reflection, and we're using a beam of light that oscillates over 200 trillion times per second. So that's over 200 trillion, I think it was 280, so almost 300. Almost 300 million samples per second are being counted, so to speak, by that detector. So even the most utterly minuscule deviation will be detected. That being said, there's all sorts of noise. Someone brought up for example, volcanism or earthquakes. Seismic activity would certainly produce an extremely large vibration by comparison to what we're talking about. So the computer brain is taking that into account. It knows of certain noise floors produced by certain things. For example, the heat of the atoms and molecules inside the optics. They keep this thing very cold in a vacuum, but it's not absolute zero.
atoms and molecules in the various components are moving. That produces noise. Normally, that kind of noise would be so minuscule you wouldn't even worry about it, wouldn't even talk about it. But when you're talking about an instrument this sensitive, that tiny amount of noise actually matters. So the computer knows, so to speak, what that kind of noise looks like, and it eliminates it from the data selectively, using, if you will, imagination. Like I said, it's kind of an artificially intelligent algorithm. And then in the case of obvious things like seismic activity, they get data from seismographs and various networks, and they can tell, oh, that seismic event obviously was not a gravity wave event. And again, that data can be tossed out. So to answer the question somewhat oversimplified, the computer algorithm, the artificially intelligent software that continuously analyzes the data, is constantly throwing out noise data so that we are left with actual useful results. Okay, that was a good question. Any follow-ups on everything I just said so far? Questions so far? Let's see if you got anything. I have no idea. That's nonsense. The thing about the music. So let's talk about. I said I was going to tell you a story. In the early 1990s, indirect evidence for gravity waves was detected, and it was part of the reason that there was so much optimism driving this project, because LIGO was so unlikely to succeed because it was so incredibly ambitious, trying to find something that should be undetectable. I mean, phenomenon that should be impossible to see. But in the early 90s, we found evidence that gravity waves exist by measuring the timing of neutron stars. Now, this is interesting. Here's an animation of two neutron stars that are spiraling into each other. Now, I like this animation because notice how it shows the starlight bending, because space-time is being bent by these two heavy bodies that are rapidly spinning towards each other. I'm going to let that play for a second. This was provided by NASA. Now, the two neutron stars are going to hit each other and explode into what's known as a kilonova. Kaboom. Kilonovas are a new class of stellar explosions. They're a type of supernova that entails specifically the destruction of two neutron stars that collide. Kilonovas are famously responsible, most likely, for the abundance of heavy neutron-rich elements in the universe like gold. You have kilonovas to thank, most likely, for the gold in your watch or your ring or any other gold you might own. Now, this particular event is not the one that was detected in the 90s, but what they did detect was two neutron stars spiraling towards each other. Now listen to this. I'm going to pause this. One of the questions that was asked in the first half of the 20th century about gravity waves, once relativity was accepted as real, they asked a profound question. Can gravity waves do work? Do gravity waves affect the physical universe in such a way that they are effectively doing work? Now, when I first heard that question, I somewhat dogmatically dismissed it as, well, of course they do. Because there's no free lunch. People who know me hear me say that all the time. There's no free lunch. If you're doing something, then there's some kind of work being performed, and that work has to have a cost. But at the time, that needed to be proven mathematically. And in the 1970s, it seemed to be demonstrated that indeed the math showed that gravity waves were doing some kind of work. But we had to prove that. So like I said, in the early 1990s, this pair of neutron stars was detected. One of the neutron stars was invisible to us, but the other was a pulsar. Now you guys might remember we talked about pulsars in a previous show. Pulsars are enormously electromagnetically powerful neutron stars that are spinning rapidly, and by random chance, the radio beam that they emit as their magnetic field disrupts material orbiting near them washes over us. And so we can observe the pulsations of the radio waves. That's where the word pulsar comes from. So we discovered something important. There was a periodicity to the pulsations of several hours. Now, that indicated that the pulsar was in orbit around another body. Measuring the various attributes of its orbit and shifting of its emissions, we were able to figure out that it was orbiting, orbited by, or mutually orbiting with another neutron star. What was so exciting, though, about the discovery was that the orbital period was reducing in duration. So what that meant was that the neutron stars were getting closer and closer and closer and closer to each other. But what was causing their orbit to decay? Well, one suggestion was perhaps
Gravity waves are robbing them of energy, and as a result, they are losing velocity and falling towards each other. This was a demonstration of the notion that not only do gravity waves exist, but they also actually do work and therefore rob energy from the bodies emitting them. Now, the heavier the body, the faster the body is moving, the stronger the gravity waves, and the stronger this effect is. To give you some perspective here, our planet Earth, as it orbits the sun, let's use this animation. Let's pretend that's the Earth and the sun. Earth does cause the sun to wobble slightly, but not nearly as much as this animation depicts. The Earth and the sun system, the two bodies together, emit roughly 200 watts. Now I'm going to repeat that just so you can appreciate this. 200 watts of gravitational energy. Now that is nothing. That is the energy of 2 light bulbs. So this helps you to understand how weak gravity waves are. The work being done by the Earth-Sun system is calculated to be 200 watts. Again, nothing. Now, our entire solar system, so that means all the planets orbiting the sun, all the asteroids, all the comets, the entire solar system is doing the work of roughly 5,000 watts. So our entire solar system is doing the gravitational wave work equivalent of roughly 3 air conditioners. In your house, you are consuming more power in one person's home. You are consuming more power than the amount of work done by our solar system gravitationally via gravity waves. Of course, we cannot measure this. This is just mathematically demonstrated. But again, this reminds us of how incredibly weak they are. However, the 2 neutron stars we just talked about, well, they're actually emitting trillions upon trillions upon trillions of watts of energy, and it's increasing constantly because they're going faster and faster as they spiral towards each other. This ends up being a non-insignificant amount of work, and this causes their orbits to decay. Just so you know, if you're wondering, well, 200 watts is not nothing, Troy. Does that mean that the Earth will eventually spiral into the sun because of gravitational wave? No, because it will take actually millions of times the entire age of the universe for Earth's orbit to decay via that mechanism. So essentially forever. Because there are so many other forces at work that dramatically overpower that incredibly subtle effect. So for example, Earth's inertial velocity around the sun and the sun's mass decreasing as it literally converts itself into energy means that Earth is actually moving away from the sun, not spiraling towards it. So the Earth is able to leave the sun, obviously overcoming that utterly meaningless 200 watts of radiation energy. I think that's fascinating. So I think it's fascinating that gravity waves can be so weak that an entire star system would only emit 5,000 watts of energy. I think that's cool. And that our own planet only emits about 200 watts. Again, this is one of the reasons why gravity waves tend to be detected associated with extraordinarily heavy and also extraordinarily fast objects that are very close to each other. Any questions about that? I think that's pretty neat. Okay. I want to know more about the laser. So it is an infrared laser that is pumped through multiple resonating cavities to a larger power. It starts out at only a few watts, and it ends up at about 400 watts, I believe. I actually wrote that down because I thought it was interesting. How many watts was that laser? It's a few hundred watts, which for a laser is actually pretty strong. And yeah, I don't have that handy, but that's something you can look up pretty easily. Do I have it? No, I don't think I do. Sorry about that. But yeah, so the laser starts out as an LED laser, and then it actually is shined through some garnet, and the garnet acts as a scintillation medium that actually increases its wavelength to that 1064 that I mentioned, which again is in the infrared part of the electromagnetic spectrum. So it's always an invisible infrared laser, although it starts out at a frequency that's half that, roughly. A wavelength which is half that. I mentioned earlier the fact that it's an LED laser is kind of cool because that means it's not very self-destructive and it doesn't use very much electricity. Yeah, so someone asked, Alex, considering large dimensions of LIGO facilities, Earth's surface curvature should be affecting laser beams trajectories, right? Yes. It is adjusted by mirrors? Yes. Indeed. And this is part of the issue, part of the reason that LIGO cannot identify the exact precise location of events. Let me show you what I mean by that. So we have here 4 different detection events. And as you can see, we are unable to pinpoint the exact spot in the universe where the event occurred. We get these kind of smears. See, this is kind of probability arcs. See that? Now, I'm going to talk about this more in a minute, because using other technologies, other observatories, it is possible to improve the accuracy very much. But due to the fact that there's only 2 detectors on a curved planet, they're 1,000 or so miles apart, there are limitations to the precision targeting of these events. So essentially, it's like knowing that somewhere in the cosmos something happened, and you have an idea of where it was, but you don't have an exact idea. By the way, notice we have LIGO, Hanford in Washington. We have LIGO, Livingston in Louisiana. And then we have Virgo. Virgo is in Italy. This is another interferometer, and this works in concert with these 2. And then the blue dots you see are different electromagnetic observatories, which can actually work with LIGO to help pinpoint, so to speak, the location in the sky where we observe events to take place. Speaking of events, we should probably talk about the first one. So the original LIGO, which is now referred to as initial LIGO, was christened, so to speak, in 2002. And it detected nothing. So I'll talk about what, I'm going to put that picture back on the screen. So from 2002 to, what was that? 2010, LIGO did not detect anything at all. And it was not considered a failure, because in science, sometimes a non-result is also a result. It informed us a little bit more about what was needed, the level of precision required to actually detect useful events. Running that experiment, we were able to see the noise floor and how much noise was produced, whether or not the computer could deal with it. Apparently it couldn't. So then we got advanced LIGO, and that is what they're currently using. And advanced LIGO did give us our first result. In the year 2015, September, we detected these in-spiraling of 2 black holes, and the black holes were 14.2 and 7.5 solar masses. And I have an animation to show you. You're going to like this. So notice the frequency counter on the bottom. This is the milliseconds of the wave. Now I'm going to pause it so you can understand something. Let me let that run. There you go. So colors: gravitational radiation, red to blue, weak radiation to strong radiation. Now, this 13.6 milliseconds, that means that that's how quickly the 2 black holes were spiraling towards each other. Imagine that. 2 bodies, one with over a dozen solar masses, one with a little bit less than a dozen, spinning that fast around each other, that their wave emission is only 13.6 milliseconds. So 13.6 thousandths of a second. And it only gets faster, watch, as they get closer to each other. They are losing energy because of gravitational wave radiation. And this is happening in a matter of days, then hours, then minutes, and then seconds. So I like this animation because it's 3-dimensional. Very often gravity wave animations are 2-dimensional, just like the old analogy with the sheet with the bowling ball in the middle of it to depict gravitational curvature. Look at this. Higher and higher frequency. They're going to pause the video here. Watch this. The 2 black holes are about to merge. Notice they're distorting each other, and then they become one. This is the merger. Yeah, someone mentioned the chirp. So that moment when they merge is referred to as the chirp because it's been converted to audio wavelengths and it sounds kind of like a chirp. And then notice how once the black hole was essentially a single object, the gravity wave ceased. Again, there has to be some change, there has to be some acceleration at work for you to emit gravity waves. Yes, it gets quiet, exactly. So again, I love this animation because it shows the event we're talking about, the gravitational detection of 2 black holes spiraling inward. But it also shows the waves in a 3-dimensional manner, which is much better, so to speak, much more accurate. Any questions about that? Here it goes again, the merger of the 2 black holes. Now let me show you the merger of two neutron stars. This is kind of a neat, this is a little more scientific, a little less pretty. Where we have here, the neutron stars depicted as density gradients. So the brighter the white, the denser the material. And what you're going to see is that the relationship between the two bodies becomes very complicated as they merge. Watch. You'll see that they're distorting each other. They literally are tearing each other apart, merging into this blob. Gravity waves become intense, and the material falls inward, and we have a neutron, essentially a heavier neutron star or a black hole. It depends on the event. LIGO has detected multiple neutron star and black hole mergers. Questions about that? Now, someone said that I lost them earlier, so feel free to catch up. Please ask questions, and I'll try to help you out. I know it's a complex, kind of advanced topic, but some of the concepts are pretty basic. Excuse me. I'm looking at the questions. Let's not continue until we get at least one more question, and we're going to keep going. We're pretty close to done. Anybody? Oh, good question. Well, so the kilonova is an explosion created by a neutron star merger. The amount of energy released is enormous, although not as powerful as, for example, a Type 2 supernova. It's a less energetic event, theoretically, although sometimes they can be extraordinarily powerful. And what's interesting is, unlike a typical supernova, the type of material ejected, I showed you that cloud of material blasted off by that NASA simulation, tends to be neutron-rich matter that we do not see being synthesized in Type 1 or Type 2 supernovas. So it's not just a difference in power, it's also a difference in what they do in their aftermath. And again, it turns out apparently kilonovas are important when it comes to the synthesis of neutron-rich matter, like, and I mentioned the most famous example, gold. Now, the event that was detected in 2017, we're going to talk about that right now, was very famous because we detected a kilonova in 2017 that was directly associated with a gravity wave event. And we were able to coordinate multiple telescopes. They were able to study this event in multiple wavelengths, electromagnetic wavelengths. So we had electromagnetic data in addition to gravity wave data. And we found that this one event produced 1 Earth mass in gold. Imagine that. We're not talking about a solid ball of gold. We're talking about a giant cloud of expanding matter, which included an Earth mass of gold. Think about that. Think about the mass of our entire planet of gold. Now you think, well, that's impossible. Gold's very rare. Well, actually, yeah, and that much gold may sound like a lot, but when you think about how incredibly vast the universe is and how most of the matter in the universe is hydrogen and helium, gold remains rare, even with events like kilonovas splashing out entire Earth masses of this stuff. Yeah. So it turns out that these events are important for the synthesis of neutron-rich heavy elements. Yeah. Ooh, that's an excellent question. What are the potential useful applications of measuring gravity waves? Let me put that more cartoonish but exciting video that NASA provided while I talk about this. I can't really hype this enough. You lived to witness the birth of a new form of astronomy, but more than that, a new tool by which humans can measure the universe, because suddenly we are not limited to electromagnetism. For essentially all of human history, all of our observations of the physical universe, including here on Earth, not just out in deep space, have been limited to electromagnetic radiation, which could take the form of photons moving through the universe, or electrons, or kinetic interaction between bodies, which again is actually electromagnetic. We've been able to infer the existence of gravity by watching things move, but we have not been able to detect it in this way until now. So until the year 2015, gravity was not in our toolbox. We couldn't use gravity, or gravitational attraction, gravity waves, to help us find the objects that we're talking about. Now this is important. The reason it's a good thing if you're not limited to electromagnetism is because not all bodies emit electromagnetic waves intensely.
In fact, some bodies do, but they're also so far away you might not be able to measure them anyway. For example, this event is a highly energetic event. Obviously, this is going to produce a lot of light, a lot of electromagnetic radiation. Not all events in the universe do so. For example, those neutron stars and the black holes spiraling towards each other, until they actually met, there would not have been any electromagnetic signature to let you know what was about to happen. You wouldn't be able to study it, and you wouldn't be able to find it. So it's important that we can now study the universe in gravity waves because it enables us to find things that are otherwise undetectable. For example, gravity waves have allowed us to find a very rare class of black holes. Let me show you some. Hold that thought. This image has a strange geometry. So, gravity waves, LIGO, Virgo, have been very successful at detecting very high mass black holes. Now, notice solar masses on the side. We have some monsters here, 60, 70 solar mass black holes. X-ray studies have been able to find black holes of a mass class above 5 solar masses, up to past 10, about 15 solar masses, which again is electromagnetism. But notice there's not much underneath the X-ray study line. There's not much under 5 solar masses. Now this is important because it turns out that black holes should exist in diverse mass classes, and yet we can't seem to find any or many below 5 solar masses. So this forced us to ask the question, do they not exist for some reason we're not aware of? Or is it possible that we're just missing them? It seems to be that we're just missing them. It seems to be that they're out there, but we're not able to find them. Because these low mass black holes will not affect the physical universe in their vicinity strongly enough for them to emit powerful electromagnetic rays that we can detect. Now, most of you probably know, black holes by definition do not emit light. And yet, ironically, they can be some of the brightest objects in nature because their incredible gravity accelerates material to near the speed of light, striking the accretion disk of material orbiting them and becoming incredibly luminous. By the way, quasars. Quasars are the accretion disks of supermassive black holes. They are the most luminous, consistently luminous bodies in the universe. Ironic, the most consistently luminous phenomenon in the universe orbiting an object that is utterly black to us because it cannot emit light, only absorb it. So it seems that low mass black holes just don't do that very much. They don't seem to energize particles enough for them to emit powerful electromagnetic rays. Enter LIGO. This chart's old, and I actually did that on purpose because I wanted to talk about it. I've had this chart for a while. We have now started to discover black holes below 5 solar masses. In fact, LIGO detected one that was only 2.5 solar masses. The reason it's left off this chart is because there is some controversy. Is that actually a black hole? Maybe it's an unusually heavy neutron star. There is a gray area between neutron stars and black holes where we don't know if neutron stars can be that heavy. Theoretically, a neutron star can be up to 3 solar masses. Beyond that, it should be a black hole. But again, there seems to be this gray area. And you guys may have heard of a hypothetical type of object known as a quark star, an object made of quarks that is somewhere between neutron stars and black holes. We don't know if they exist. LIGO and other gravity observatories that come after it, gravity wave observatories, may be able to detect these weird objects, these low-mass black holes and or quark stars, if they exist. So again, the reason that's a big deal, these are objects that were otherwise completely undetectable. Because gravity is now within our observational toolbox, we're able to detect things that emit no light, or things that are so far away that the light they do emit is too dim to measure, or things that are hidden from our view by light years of gas and dust. The universe is not empty. It's actually largely opaque when it comes to galaxies, for example. A black hole can hide in a galaxy. You may not be able to find it if it's hidden from your view by literally tens of thousands of light years of gas and dust. But gravity doesn't care about that. The gravity waves will propagate right through that gas and dust, almost like it wasn't there. Although we do know it does a little bit of work, so that gas and dust will move a little tiny bit, because the gravity waves move through it. That's kind of cool. Because again, like I said earlier, it turns out gravity waves can do work. Questions about that? Yeah, so someone's talking about the red nova in 2022. We're expecting this star system that Mr. Wanderlust here, or Valkyrie maybe, person here. This
this particular binary is calculated to collide next year. It's going to be cool if it happens. And it shows you how good we're getting at these measurements, that we can actually detect the inspiraling with such high precision. That might be something that one could detect with a backyard telescope. We will see. That's a good example. I'm glad you brought that up. Thank you. All right, we're a little over time, but this is a dense topic. I was expecting a little bit of discussion about this. Let me finish my thought about that famous kilonova that happened in 2017. Check this out. That's a good segue, actually. Let's see here. I'll just skip. You know what? Here. It doesn't work either. What's going on? The computer is going crazy. Hold that thought, my friends. My computer has decided to lose its mind. All right, so this is a pretty cool thing. Remember how I mentioned that the precision of LIGO is quite limited? Well, if you have different observatories working together, maybe they can improve the accuracy a bit. So notice we have this big area where we think it might occur, this big arc. The Fermi telescope integral, which is a gamma ray observatory. By the way, let me show you. This is the integral gamma ray telescope. Brief tangent, because it's pretty cool. This instrument cannot detect gamma rays directly because they're too powerful. It would destroy its sensor. So it uses a scintillator that actually converts the gamma ray impacts into ultraviolet light, which it can detect. So this is actually a gamma ray space telescope. Again, it's called integral. And it is able to observe essentially exclusively extremely, extremely, extremely violent events in the universe, because only very, very violent events emit lots of gamma rays, because you guys probably know gamma rays are at the top of the electromagnetic spectrum. So when we see an event like a gamma ray burst or a flash of gamma ray light, we know something violent has occurred. So in the case of that chart I just showed you, you saw that we had helped to pinpoint the position of an event right here using data from integral and also LIGO. And what's cool here, this image was taken from an all-sky survey. Now, if you guys don't know what that is, there are many robotic telescopes all around the world that are literally constantly observing the sky and taking pictures of it. So it's not surprising that we have an image of this random galaxy. This is a galaxy. It's an elliptical galaxy. And this was taken 20 days minus, see that? So 20 days and a half before the event. This image was taken 10 hours, or let's say 11 hours after the event. And notice there's a change. We have this dot here that was not there in that 20-day-old image. So we were able to confirm this kilonova, which again was the collision of two neutron stars. Not just in gamma ray, not just in gravity wave, but even visible light. And infrared too. Technically, a regular person with a large backyard telescope and good imaging equipment probably could have detected this. They wouldn't have known to look for it, of course. You'd have to tell them, hey, turn your telescope over here and look at this right now. But it's technically possible that this event was so luminous that you could have actually detected it with ordinary off-the-shelf equipment. I think that's pretty fascinating. Any questions about that? No. So someone asked, is the speed of gravity based on the high frequency or high hertz? No. Gravity moves at the same speed as light, 300,000 kilometers per second, 186,000 miles per second, or more accurately, the propagation of space-time itself is limited to the speed of light. It is a fundamental aspect of this universe. Now, this is cool. You're going to love this. Speaking of what you just said, the light arrived late. We looked at all the timestamps from all the telescopes, and the light arrived over 1 second late. The gravity waves got here first. Does that mean gravity waves are faster than light? No. It means that the light was delayed because the light had to go through a bunch of material between us and the galaxy and was slowed down very, very, very slightly by it. Whereas the gravity waves moved through any obstructions with impunity. They didn't care. So that's kind of neat. And so even though gravity waves and light move at the same speed, air quotes, apparently gravity waves often appear a little quicker because they're less affected by obstacles. I think that's fascinating. Any questions about that? I think that's a cool story. And again, that was in 2017. Yeah, so, by the way, that's not the only, this is actually a tangent I find fascinating. It's not the only example of delays in the arrival of things. For example, there was a famous supernova in the late 1980s in the Large Magellanic Cloud, and we received neutrinos, which are ultra-low mass particles which are emitted at the speed of light and in large numbers by nuclear reaction. We actually monitored neutrinos from that supernova before the light of the explosion reached us, and for the same reason. Neutrinos, because they're able to pass through regular matter without stopping, were not delayed. But the light was delayed because it had to blast through the enormous shell of gas and dust being ejected from the dying star. So, again, a few seconds of delay was incurred because the light had to go through something. Again, I think that's pretty awesome. Yeah. That's an interesting question. Gravitational lens increased the distance for light travel. Yes, and I'm sure that was a component of the delay. That's right. I didn't want to get into that too much because then it creates this can of worms. But wait, wouldn't the lensing be attached to the gravity waves? Wouldn't that cause all sorts of connections and maybe the speeds would be the same? Blah, blah, blah. Yeah, I don't want to get into that debate because I'm not actually qualified to have that debate because we're talking about an incredibly nuanced shift in the velocity of the light. You know, so you would have to do some big math in order to actually have a meaningful conversation about that. All right, so what's the future? What do you need to build? If we want to improve our ability to detect gravity waves, what do we need to build? What do you think? Someone tell me. What do we need to build if we want to do even better with gravity waves? Please avoid big math tonight. Yeah, no problem. So, think about it, guys. What do we need to build if we want to do even better gravity waves? More locations? Yes, that would increase the accuracy of our ability to pinpoint where in the sky these events happen, but it would not increase our sensitivity. So what do we want to do if we want to increase our sensitivity? Oh, by the way, just in case we're not clear on this, LIGO is amazing, but it is limited. Currently, all of the detection events involve the most heavy, most violent, most speedy objects in the universe. We're talking about black holes and neutron stars spiraling into each other and exploding. It's only detecting the most violent, most powerful, most extreme, most consequential bodies. So if we want to detect less consequential things, what must we do? Oh, bigger. Someone said bigger. Very good. Oh, hey, good. And someone said essentially the same thing. Build detectors in space. Exactly. Check it out. I was hoping this image would have better geometry. I didn't bother adjusting it. That's fine. I'll just do that. So this is LISA. And of course, this is a drawing. LISA is a space-based gravity wave observatory. Same concept. We have lasers doing the exact same thing. Essentially, it's an interference, or in this case, a interferometer. However, not better lasers emitted by devices that are much farther apart. So instead of a few thousand miles, how about a few million miles? So if you have a separation of millions of miles, you dramatically increase the sensitivity of your detector. This would enable us, theoretically, to detect a lot more events and bodies that are less extreme. And then in the far future, maybe 100 years from now or more, we might invent a gravity wave observatory that is so sensitive that it can detect gravity waves which were emitted by the very young baby universe prior to the end of opacity. And if you don't know what I'm talking about the period prior to the cosmic microwave background. Let me show you what I'm talking about. I'm sure I've showed you this picture before. WMAP. This image is getting pretty old now. There are better versions of it, but I happen to like this picture. So WMAP, the Wilkinson's microwave anisotropy probe, is a map of the entire sky in microwave wavelengths with an extremely high contrast. The dynamic range of the detector is extremely high. And so it was able to reveal that the microwave background left over from the Big Bang is not uniform. The problem with this data is it's not actually allowing us to see the moment of the Big Bang, but rather a time millions of years after it, when the universe essentially cooled down enough and became
low enough in density for photons to finally escape whatever atoms were emitting them and fly around in space. So prior to that time, in what we call the cosmic dark ages, you couldn't observe the cosmos because photons were not able to move freely through the cosmos. So this is a perfect example of where gravity waves are a terrific tool, because we're trying to observe a period in the history of our universe where electromagnetic waves were not being emitted in such a manner that we could detect them. So some futuristic, amazing, super sci-fi gravity wave observatory, hopefully built in the next century, will be able to study the universe and gravity waves emitted prior to this light's emission. Maybe we'll be able to look back to only a few years after the Big Bang, a time that was ordinarily thought impossible to observe because of this problem, because of the problem of the cosmic dark ages, when there was no free photon movement. So that's pretty profound in my opinion. Gravity waves may eventually enable us to look back to the very, very, very beginning of the universe. We like to say that we've done that with the WMAP, but we admit that it's not actually the very moment of the Big Bang, but a few 100,000 or a few million years after it, because of this limitation of the ability of photons to propagate. I think that's a cool story. Questions about all that? I'm going to put this picture back on the screen because I like it. All right, we went over time again as usual, but I don't care because it sounds like we're interested somewhat in this topic. I want to repeat. I don't remember who said it, but someone said I lost them. So if you're still lost, please let's fix that. I don't want you to leave with more mysteries than you started with. So let's ask some questions. Let's do 8 minutes. We'll stop at 8:30. How's that sound? Or maybe sooner if I don't get anything. Put in locations around Earth's orbit around the sun. Sure. I mean, that's one of the things we could do. That would actually be fairly easy to do. So, just a little history summary for you. In 2015, it was the first direct detection of gravity waves, and it was achieved by Ligo. And if you're a Washingtonian, happened right in your backyard, that's cool. If you're someone from Louisiana, same thing. If you're from Italy, Virgo contributed a lot as well. That's the same idea. So this is something you can go visit. I have some friends that work at Ligo, and before the virus hit, I can tell you that they have a very generous visiting program. You can go and they let you take a tour of the facility and actually enter the control room, and you can see the live data coming in all the time. You can actually watch the data from the interferometers coming in on big screens. It's pretty cool. So I recommend it as a tourism destination if you're trying to learn a few things. It is cool that you get to be visiting a facility that is on the cutting edge of science. I want to repeat. I need to hype this up. This is a new form of astronomy. Never in all of human history have we been able to study the universe via gravity waves. Suddenly, we are no longer limited to electromagnetism and neutrinos. Questions about that? What is the fourth dot in the SWOPE plus 10.9 H image? Fourth dot. Let's see. What is the fourth dot in the SWOPE 10H? Well, this image is clearly better exposed than this one. Are you talking about a star? Because there's probably more stars being exposed. Is that what you're saying? The new one is the explosion. This dot here with little targets on it. See, it's completely missing 20 days prior to the event, and it's obviously there 10 hours after it. Is that the fourth dot you're talking about? Now that we've detected gravitational waves, do we understand how gravity works? I mean, we can pretend we do. We can say with a straight face that gravity is the manifestation of the curvature of space-time. But of course, there's all sorts of mystery wrapped up in that phenomenon as well. For example, we still don't know if the graviton exists. We tend, when we're discussing various physics, when we're within different contexts of physics, we tend to assign particle or wave characteristics to quanta of energy, but we don't know if gravitons exist. So the answer is kind of to your question. That's funny. You have been to one of those Ligo places, yeah. I recommend you go to one. It's a cool thing. Questions. We got 5 minutes. Let me look at my moderated chat, see if I missed anything. Any recommendations? Is that a word? Any recommendations for fun astronomy telescope-based experiments? Experiments. Well, if you want to spend time and money, imaging things is always fun or difficult, challenging. You'll find that looking through a telescope is easy,
But taking pictures of space objects, that's a whole other ballgame, and that involves having a very strong mount that can track the sky with high accuracy. However, if you do try to do it, you'll find that you can image objects that are completely invisible to you using visual astronomy, because human vision is quite weak when it comes to looking at this incredibly dim ancient light. Oh, but kind of within the context of what we talked about tonight, hang out on, like, I don't know, Facebook pages about astronomy news, or I don't know, message boards or blogs, or what am I trying to say, podcasts, because every now and then we'll detect a supernova explosion in another galaxy, and you can see it with a telescope. I've done that twice in my life. I've seen 2 supernovas in other galaxies, one time right here at the observatory. And it was quite exciting to literally witness the explosive death of a star. You actually can see one roughly once a year somewhere in the entire sky, not with the naked eye, but with a telescope. There's a supernova explosion somewhere in the Milky Way galaxy roughly every century, but it doesn't mean you're going to get to see it, even if you're lucky enough to be alive when one occurs, because it may be behind, like I said, tens of thousands of light years of dust and gas, and you may not be able to see it. The Milky Way has had many hidden supernovas. We find their aftermath, literally millions of years after the fact, and sometimes sooner. But we realize that many of these supernovas would have been hidden. Ironically, it's easier often to observe supernovas in other galaxies because your view is not obstructed. So that's a fun thing you can do with a telescope, in my opinion, looking at a star blowing up millions of years ago. Speaking of time, because gravity waves are limited by the speed of light, just like everything else, when we detect an event in gravity waves, it didn't happen yesterday. In the case of the first detection, the pair of black holes that were spiraling in towards each other, they were 1.4 billion, with a B, light years away. So that event that we detected in 2015 occurred 1.4 billion years ago. So just like when we look back in time with light or electromagnetic telescopes, we are not seeing the universe as it is now, because the speed of light, in a cosmic sense, is surprisingly slow. Even though light is very fast to us measly humans, when it comes to traversing these extraordinary distances between galaxies, it takes a long time to get anywhere. So you are literally looking back in time millions or even billions of years, depending on the object. Questions about that? Yeah, so that's a kind of a tangent, Ed, but Ed's bringing up what we call quantum entanglement, or what Einstein called the spooky action at a distance. He's right. The reason that's such a big deal is because it seems to defy all of these understandings about the speed of light being absolutely sacrosanct, and it can't possibly be defied or exceeded, and yet quantum entanglement between particles seems to completely ignore space-time limitations, which indicates that the particles in the case of quantum entanglement might actually be the same particle occupying 2 spaces at once, which is mind-boggling, mind-blowing. Yeah. All right, here's someone raising a hand. So Washington State Parks, Goldendale Observatory is kind of a worst-case scenario for reopening because it's an indoor experience. People come from all over the place. They touch everything. We could have opened with very small numbers, but we felt that it was important to not open until, by the way, with advance notice only. We want to reopen when it's okay to do so with a reasonably sized group. Once we can do that, we will hopefully resume operations in a semi-normal fashion. But if we do that, in the short term, we're probably going to do an appointment-only model. I don't know when we're going to resume fully normal operations, and I think many business owners are asking the same question, about other types of locations and museums and eateries and things like that. So I wish I could give you an answer about when we're going to open, but I don't have one yet for you. Sorry. Did the collision of neutron stars create other heavy elements? Oh, sure, yes. Many heavy neutron-rich elements. I think another one was, I don't remember off the top of my head, platinum? It might not be platinum, but there's a few other famous heavy elements that were synthesized in large abundance by that Kilonova event. So no, the 1.4 billion light years distance measurement is actually more based on the weakness of the signal, so to speak, because just like with electromagnetic phenomena, the closer the event, the more energetic it seems via gravity waves. So we were able to study, or we were able to detect the mass of these 2 black holes with high precision by studying the timing data. And so we knew how
energetic the event should have been, and then we were able to compare that to how energetic it appeared, and it gave us this ballpark estimate. And by the way, there could be a 20% margin of error in that 1.4 billion light year distance requirement measurement. However, one thing that was cool about the event, it was confirmed with 99.9% certainty to be a gravity wave event and not random noise. And part of the reason for that is because not only did it behave the way we expected at LIGO in Hanford, there was also a delay between the data in LIGO in Hanford and the LIGO in Louisiana because it took time for the signal to go from one facility to the next, because even though it's 1,000 miles, that's enough of a distance, or more than 1,000 miles, that's enough distance that there would be a measurable delay. In fact, for a device as precise as LIGO, that's child's play in terms of determining delays. Yeah. All right, so let me read through these real quick, and I'm going to wrap it up right now. Actually, let's see. Looking forward to solar as we pass solar. Yeah, so the sun is waking up. We're starting to enter the next solar max. I can't wait to start taking videos and pictures of the sun again to share with you guys. Most of my content that I share with people for the solar shows was taken a few years ago, back when the sun was active. You guys know the sun has an 11-year activity cycle, which has been on a downward trek over the last few decades. And so the solar minima that we just had was incredibly minima. I mean, it was so so minimal that there was essentially nothing going on for months at a time, and it was very boring to look at the sun. Oh, darn. Yeah, so I agree. I'm also looking forward to the sun waking up. Let's see. Hey, I think we did it. We got through all the questions. This was a very advanced topic. I hope everyone who's watched this video understands a little bit better how gravity waves work. I hope you have a little bit more appreciation for the technological wonder that is LIGO, which again is possible not just because of the clever use of lasers and mirrors, but also powerful supercomputers that can analyze the data and find useful information amidst a great deal of noise produced by just innumerable sources. Yeah, so very impressive. Yeah, good. So next week we're going to talk about telescopes, talk about the types of telescopes, how they work a little bit. Probably mostly electromagnetic. Well, actually, wait, that's the silliest thing to say. Essentially, all of the telescopes we're going to talk about next week are electromagnetic telescopes. But that's a pretty broad range, isn't it? Because the electromagnetic spectrum is broad, and we have all sorts of things that can be observed. Essentially, we have telescopes for all these wavelengths, although not all of them can be operated on Earth. Yeah, we'll talk about why that is. Yeah. So, I have no idea why the fading in and out has suddenly become slow, but I hope you found that artistic. Again, I hope you guys found this show illuminating. I hope you appreciated the gravity of the situation. And hopefully we'll find something else interesting to talk about next time I see you. So everybody, stay safe, stay healthy. If you had a good time tonight, please like and subscribe. Tell your friends. And I'll see you next week.